And today, at first, I want to discuss how to deal with the qualitative variables. So, okay, so last time we finished 3B, so we start with the slide 53. So this is an example, so sample data set of, I think the house price in Troy, Michigan. Yeah, and we have several variables. So the first variable, we don't really use it, but this is date, and this is actually the exact date, such as October 10th in 2022, but actually it's represented as integers. Maybe one is January 1st, 1900. So it does not make sense in this data set, but we ignore this. And price. So this is quantitative. And style. So this is the factor variable with 5 levels: by level, bungalow, and maybe colonial, ranch, and I don't know the other, but maybe split. So we have some, and we have 5 levels. So I think the 3 means the 3rd level. So maybe, I don't know, maybe colonial. I think because this is dictionary order, in dictionary order. And square footage and year and number of bedroom and number of bathrooms. And here our focus is the number of bedrooms. Okay, so all variables are useful to explain price, but the number of bedrooms can be treated as categorical and also numeric. So it makes sense that 6 bedrooms is twice as many bedrooms as 3 bedrooms. So we can introduce it as a quantitative variable, but also, the price may not be linear. For example, if up to 3 bedrooms, the more bedrooms is better, but the 4 bedroom or more is unpopular, for example. So that is possible. Or people just don't think they don't need more than 5 or more bedrooms. So it's not really clear if this variable, so the number of bedrooms, has linear relationship with the price. So we would see how these are different. And our strategy here is this. So first, we introduce the number of bedroom as quantitative variable. So this as numeric. So we assume a linear relationship between the number of bedrooms and the price. And then we add another factor. This is a factor variable. So we consider nonlinear relationship between the number of bedrooms and the price. So basically the base model at least include the number of bedrooms as numeric. So this has only degrees of freedom of 1. So this is just one parameter. You can see the B4 is a parameter. But if we introduce factor variable, we have the number of bedrooms either 0, 2, 3, 4, 5, or 6. So we have 6 levels. But of course, we have intercept. So the baseline is 0 bedrooms. So we have 5 degrees of freedom. But we have another parameter, beta 4 here. So basically, this factor have 4 additional parameters, 4 additional degrees of freedom here. So our null hypothesis is here and the alternative hypothesis is here. So at least the number of bedrooms has some information. So that is our assumption. And we wonder if nonlinear relationship between the number of bedroom and the price is a significant factor to improve the model. Yeah, so in this case, yeah. And okay, so we fit the model. So the base model is here, only bedroom as numeric. And then, yeah, we define the number of bedrooms as factor, and we add this factor again. Then here is the result. Here is the null model. So number of bedrooms as just numeric variable. So you can see that this is the negative 8.8 times 10 to the power 10 to the third power. So that means the negative 8,837. So that means the one additional bedroom means the $8,800 less than yeah, actually the additional bedroom makes the price $8,800 lower. And okay, so this is the at a glance the contradictive, but actually this is the consistently negative parameter in many data sets. And that is because we have already considered the square footage, year, and the number of bathrooms. So then more bedrooms means what? The more bedrooms means just we have small boxes, right? So no other expensive features, probably. So the bedrooms are just boxes, so it's cheaper to develop. So actually, given the same square footage, year, and the number of bathrooms, the number of bedrooms usually have the negative impact on the price. So actually, this is right, and this is significant. It's yeah, I think reasonably significant. So p-value less than 0.01. And the number of observations is what? You can see we have 5 parameters. So still the 485 degrees of freedom for residuals. So 490 observations. That is our case. And okay, so this is one model. So number of bedrooms is at least a useful predictor to determine price. And this is the full model. We introduce the factor variable. And okay, so 0 bedroom as the baseline, that we have 2 bedrooms, 3 bedrooms, 4 bedrooms, 5 bedrooms, and 6 bedrooms. But since we have already have the quantitative variables, we should have only 4 additional parameters, right? So if we have 5 additional parameters, then we have the redundancy, right? So basically, in addition to baseline, we only have the 5 degrees of freedom, right? So, but we have already used one. We have already used one for the quantitative variables. So we should have only the 4 additional parameters. So that's why this is not estimable. So it is reported as NA. NA basically means this variable can be expressed by a linear combination of other predictors. Okay, then what happened? So here actually the parameter changes a lot. So negative the 31,000. So previously negative 8,000 or 9,000. Here 31,000. So it's the it's much smaller value and it's significant. Okay, but actually it's canceled by these parameters. So number of bedroom, if the number of bedroom is 2, then actually we add $83,000. So okay, so think about this. So at first, the number of bedrooms are 0, 2, 3, 4, 5, 6. And if 0, what happens? Then the contribution of this is equal to, of course, 0, because nothing. And how about 2 bedrooms? The contribution is the number of bedrooms times 2. So 2 times negative 31,000 and plus 80, about 84,000. So actually the contribution is, okay, so this contribution is 61K, 62K, so negative 62K plus 84K. So actually positive 22K. And number of, so 3 bedrooms, what happens? So our effect is the 3 times negative 31K plus the 109K. So that means negative 93 plus 109, so positive 16K. So actually the 3-bedroom houses are $6,000 cheaper than 2-bedroom houses. And 4 bedrooms, 125, so the 3 times 31K plus 125K. So that means what? Oh, sorry, the 4 times. 4 times negative 31, so negative 124 plus 125K. So this is 1K. So actually the 4-bedroom houses are $15,000 cheaper than 3-bedroom houses, and so on. 6 bedrooms. Yeah, 5 is the, again, the 5 is the 5 times negative 31K. Plus 169K. So 155 plus 1969. So 14K. But we only have a few observations. So I think probably we have some exceptions. And the 6 bedrooms, I don't know. So this is NA. So I think this should be ignored. And that we have, yeah, strangely, yeah, so negative 186K, I think. So
Did
this
the
is
data
strange,
include 6 bedrooms?
Yes, only one observation. Yes, only one observation of 6 bedrooms. Yes.
Oh, okay.
Yes, here.
Ah, okay.
Yeah. So it's.
Do we apologize, but do we have to have factor bed and not factor bed?
Oh,
variable
you don't really
bed.
have to include it. Yeah, that's true. So you don't really have to include this. Then you get more natural result. I think that this, the accuracy for the estimate for 6-bedroom is sacrificed here. So only one observation, and it's sacrificed. So that is one problem. But the here objective is that we see if this has additional information to this. Yeah. Sorry. So yeah, this is a little bit strange, but yeah. Yes. So actually, this effect is. Oh, sorry. Yeah. Yeah, I don't know exactly what happened, but actually this is the case, and I think yeah, I think probably it's not the best way if we include this. So we are testing the significance of these factors. So if these factors is significant, then probably we should drop this quantitative variable and make the fair estimate for B2 to B6. Probably that's a better way. But here, our objective is whether this is enough or not. Yeah, but actually, when we see the p-values, then we can see this is probably significant. You can see that 0 and 2 are, the 2 bedrooms is closest to the 0 bedrooms, but still the difference is pretty large. So $84,000 the more than 0 bedrooms, except for this effect. So so this difference is pretty large, and the standard deviation compared to standard deviation, this estimate is large. So we can see that the 0 bedrooms and the 2 bedrooms have different coefficients, we can see. So yes. So
I guess I apologize. I have to look at the data again. 0 bedrooms, I'm assuming, would be a studio, but there is no 1-bedroom listed?
No, actually, in the data set, only the 0 and 2, 3, 4, 5, 6. Yes.
Oh, well, that answers the question.
Yeah.
Guess that okay, thank you.
Yes. Yeah, so the number of 2 bedrooms, actually the total effect is calculated here, but this coefficient is significant. That means the 0 bedrooms and the yeah, it's hard to say, but except for linear terms, that we have some additional effects we can see. And also some other factors, these are also large. So at least at this point, we can see that we have to distinguish 0 bedroom houses and the 2 or more bedroom houses. So probably the conclusion is we should include this factor. So probably we drop the quantitative variable and we put the full factor variable. So bedroom as factor variable. Actually, I didn't really show the result here, but that is the fact. Maybe I should have shown it. And that can be seen in ANOVA more clearly. So this is sequential test. So to see which factors are important, and so sequential. So basically, we consider the price on intercept first. Then we fit price on square footage. And we compare this null hypothesis against this alternative. And the p-value is here. So very small. Or I would say that, sorry, the square footage, square footage. So this p-value. So it reduces the error size significantly. And the next is year, so that we compare price on square footage and price on square footage and year. So basically, we are checking the significance of year, assuming that square footage is a useful predictor. And actually, this is significant. And you can see that all predictors are significant in this model. So that means that we should include the number of bedroom as a factor variable rather than just quantitative variable. And the number of bathrooms, maybe also the same theory applies. So maybe we should check if the number of bathroom there works better as a factor variable, or just this is enough. But yeah, we have to see. Yeah, then later, I think that we have to remove this bedroom as quantitative variable, and we should estimate all of these 5 coefficients. Probably that is more natural way to estimate it. So in this estimate, this NA makes probably the error for the 6-bedroom house very large. So that data is reflected in this coefficient a little bit, but probably this is not the best way to estimate the entire model. So probably we can estimate it again. And that's it. Yeah. So in this way, we can see if some variable should be quantitative or categorical. There are many other ways to estimate it. For example, we introduce bet as quantitative variable, and another maybe square of bet as the quantitative variable, and cubic cube of bet, and so on. So that is another way to go. So that means we have maybe, yeah, so linear term and quadratic term, it makes sense because the quadratic function have the, local, the global maximum or global minimum. So if we have such a number as the best number of bedrooms, then fitting quadratic function makes sense. Yeah, also we can use the AIC to compare the model with only bedroom as quantitative or bedroom as factor variable. And we have 4 more parameters. So if 4 parameters are all useless, we have the penalty of 8. Penalty of 4 times 2, so 8 in AIC. So if these 4 variables are useless, then this becomes 11,797 plus 8. So 11 maybe 805.75. But actually it gets smaller. So yeah, significantly smaller. So 18 smaller. So we can see that the this model, the latter model is better. Model 4 is better. Yeah, same analysis can be done for number of bathrooms. In fact, the number of bathrooms as a factor is also a significant predictor of price, while the result is not shown in slides. Yeah, usually the number of bathrooms has consistently a positive factor to increase the price. Here, the number of bathrooms, the $10,000. If you have 1 additional bathroom, basically that house has $10,000 higher price tag. Sometimes this estimate is like the 30,000, maybe 10,000 to 30,000. I have seen. Yeah, so that's reasonable. So we have to do many things. Just the toilet is $100, but we need some work to get water to the room. Especially it's hard in the basement or something. So it's higher. And you can see the square footage, $111 higher. This is old data. So usually now, the 1 additional square footage costs $200. But here, the $111. And year, $833. So if 1 year newer, $833 higher. That is very small amount. So yeah, but basically, I don't know. But the Americans don't really care about the year the house is built. Yeah, it may be reasonable, may not be reasonable. I think I don't know. If the construction cost is the $80,000 and it lasts for 100 years, then it's pretty reasonable. But I don't know. No, probably it costs more, and probably it's 100 years maybe. You can use a house for 100 years, but I think in Troy usually the 60-year-old houses are already torn down. Usually people rebuild. So I think probably $833 is slightly too small. But anyway, so this is the estimation result. Do you have any questions? And yeah, AIC is the theoretical quantity. We assume that the normal distribution in the regression model and so on. So yeah, so errors are independent and so on. So I think this isn't really very reliable indicator to determine the model. So we will study later, but the more simulated simulation-based methods such as cross-validation is recommended to compare the models. Yeah, so AIC can be calculated quickly if we have the likelihood function. So yeah, this is one good statistic to see, but realistically, in practice, maybe we should try cross-validation if this analysis is more serious. Yeah, so that's it. And do you have any questions? Okay. And today, who is here? William and Hunter. Oh, Hunter, congratulations, you passed the master's exam. Or if you are a master's student, and if you are in the last semester, then you have to take the master's exam. I think the color sent you the notice in the maybe early January. So just make sure. And Erika and the Nicholas. And James. Tawhid. Sorry. Okay. Okay, so that's it. And the remaining part is just a few remarks, maybe conceptual remarks. So we have been estimating the linear models, but sometimes the linear assumption is not satisfied. I mean, in terms of x, that this is a linear function of x to explain y. But in general, that we want to have this kind of models. But this is still a linear model because it's linear in terms of parameters. So beta 0, beta 1, beta 2, beta 3. This is a linear function of betas. And estimating beta is the main topic in statistics. So as long as this is linear with respect to betas, it should be fine. Yeah. Of course, more complicated model is possible. For example, the beta naught plus beta 1 x1. You know, just this is the same model, but if model looks like this, then it's not linear with respect to coefficients. Yeah. So this is not a good parameterization, but sometimes, you know, beta isn't really, you know, sorry, the right-hand side isn't really a linear function of beta. For example, maybe one typical example is maybe exponential of beta naught plus beta 1x. This sounds reasonable model, but in this case, this model isn't right-hand side isn't a linear function of betas, beta naught and beta 1. Yeah, but as long as the parameter is, the model is linear in terms of parameters, still we can estimate the model in the same way. And this, the product of x1 and x2 is called the interaction or two-way interaction term. If we have x1 square x2 or x1, x2, x3, then that is three-way interaction. And here is one example. So intercept, we are fitting sales on intercept and advertisement in TV and the advertisement in radio. These are dollar amount and interaction between TV and radio. And actually these are all significant predictors. So the product of TV and radio matters. So probably we have positive effects if you make advertisement on both TV and the radio. So people notice that, okay, so this company is a really large company when you see the people see the advertisement in both TV and radio. And some other reasonable existence of interaction terms. For example, in agriculture, the crop yield may be affected by the amount of fertilizer only when sunlight is not enough. If sunlight is enough, then anyway, the crop yields is high and the crop grows in a healthy way. But if sunlight is not enough, we need fertilizer. Yeah, that makes sense. Or in the baseball, the southpaws pitch well only when the batter is left-handed. So that is possible. Right? So there may be, southpaw always pitches better than regular right-handed people pitchers, but probably that is just the matching problem. So southpaws pitch only better against the left-handed batters. Then we can introduce interaction terms. Any questions? And people's finding is the linear term is most of the time most important, and the secondary, the quadratic term is second important, and the cubic term third important, and so on. So usually the model, if we have three variables, the beta x1, x2, x3 are all not important, and the best model is beta naught plus beta 1 times x1, x2, x3. This does not happen often. It's possible, but it does not happen often. And I don't know what's the problem here. Maybe the cubic term is a problem. Maybe if we take this cubic root of the product, maybe it behaves better. So I don't really know, but the usually linear term of x1, x2, x3, those are more important than higher order terms. Next, the 3 nearest neighborhood, k nearest neighborhood, and linear regression. Yeah, so k nearest neighborhood. So remember that this is the decision rule that based on the k closest observations to determine the predicted value of at x. Yeah. Yeah, so we have discussed it as a classification algorithm, but it can be used for regression problem also. So to be exact, to estimate the f hat of x naught, that we just take the average of the k nearest terms. So if we have, so we have the x1, y1 to xn, yn, maybe x100, y100, and we have x naught. Then we choose the k closest observations to x naught. So if k is 5, then suppose that the x20 and x23 and x40 and x65 and x80 are closest, then we take the average of corresponding y values, y20, y23, and y80. So this is the estimate for y0 hat. So this is the way the k nearest neighborhood works for regression model. Yeah. So k nearest neighborhood is pretty natural way of thinking. For example, when stock market people make a stock market prediction, and sometimes people do some technical analysis. For example, in the past 5 days, the returns are, the prices are going up for first 4 days and suddenly dropped. Then next day it's likely to be positive return. So they look for the same pattern in the past data set. So that means the in the 5-dimensional space that we are looking for the similar data points in the past. Then based on those data points that we predict the tomorrow's stock market return. So that is, I don't know if this is a good model for this specific case, but that is natural way of thinking. So it's pretty the natural model. And when we have more than 2 predictors, then the fitted curve of k and n looks like this. So we take just average. So if the 5 nearest observations are the same, then the value is always the same. So you can see in some restricted area, actually the y hat, so estimated value of y is flat, so it's the same. because these points in this area, so 5 closest observations are the same, so that we have the constant value. And this is larger K. I think the larger K. This is case actually 1, and this is case 9. So larger K, the more smooth the stable surface. But of course, if K is equal to N, just we have a flat surface. So that is too high. So that K is too large. So somewhere we have the optimal number K. In this case, even K is equal to 1 looks fine. But larger K, smoother, but higher bias. Or smaller K, we have large variance, but smaller bias. So there is some optimal K for prediction. Okay, so that's chapter 3. So still conceptual, but for linear regression that we covered the tangible materials. Yeah. Do you have any comments?
This is kind of miscellaneous, but I know we talked about, so when we say linear regression, we always minimize the sum of square distances, where the distances that we're referring to are the vertical distances.
Yes.
And I know you said, okay, well, maybe we could take the horizontal distances, but then we're really just regressing X on Y. So now my question is there ever a time where we try to construct a best fit line where we just minimize the sum of distances, where the distances taken are just the shortest distance between each point in the best fit line? Or maybe that's just more. I mean, I feel like
I think it's
much more
possible.
Yeah,
that's a good question, and I think that's possible. Yeah, so the people think about the equation first, so that's why the error term is either. So we think about the model, right? So the y is equal to ax plus b plus epsilon, or maybe we can think about the other way, x is equal to ay plus b plus epsilon. So because of this, that we only think about horizontal or vertical distances, but the distance to just the straight line. So that is possible. Yeah, that's interesting question. Yes. If we think about the geometric meaning, that is most natural. That's true. Interpretation of error is a little more complicated, maybe. X has measurement errors. That may be possible. So usually, the people think about in this way. So this is a kind of the error to observe y, and x may have some error as well. So in that case, y is equal to a times x plus zeta plus b plus epsilon or something like that. And in this case, probably still the optimal a and b are not determined by this, right? Because we have a times c or something. So in regression context, I don't really see this method, but I think it's interesting to interesting to look for the existing studies. That's possible. Yes.
Yeah, thank you. I feel like my guts tell me it would be much more computationally involved than simple linear regression, obviously,
Yeah, sure. Sorry, you mean the simple regression is much easier, right?
That's what I was thinking in terms of just how long it takes to compute, just how long it takes to construct the model itself.
Yeah. That maybe, that's true. I don't know. This is high school students problem, right? So x and y and the shortest distance, and we have some algebra to solve just the equation. Yeah, sorry, I haven't thought about it seriously, but yeah, that's another possibility. Yes, that's interesting. Yeah, it can be useful in some context. Yeah. Yeah, that's true. X and Y. Yeah, I think probably this assumes that the X and Y has the same amount of measurement errors or something. So that is reasonable or not, I don't know. So yeah, maybe some reason that it's not popular. Yeah, so vertical distance and the horizontal distance have the same error size. That isn't really reasonable assumption if we haven't standardized X and Y, right? But once you standardize X and Y, probably the slope isn't really an issue. Slope is just the correlation. So yeah, that is probably why it's not popular. Yeah. Yeah, it's interesting thinking, but yeah. At least it's good that the fitted line is unique. So yeah. Yeah, probably that's the reason. So epsilon is the error for y, and the horizontal distance is the error for x. And if we take the Euclidean distance between this and this, then that means that we give the same weight for the error for x and error for y. And why the same weight? Probably we don't have enough situations for that. Yeah, that's an interesting question. Do you have any other questions? Anyone has any other questions? Okay, so chapter 3 lab. So this is just an application. So I do some regression analysis in R. So this is Boston dataset, Boston house price data. And we have predictors, crime. Okay, so at first I want to explain this. So this has the 506 observations, and we have 14 variables, I think. And the sample unit is town. So Boston suburb have 506 towns. And then we have variables, and basically the last one is the response variable. So median house value in the town. And surprisingly, the unit, can you guess the unit for this? Of course, the unit is US dollar, but actually this is the 1,000 US dollar. And okay, so in this town, the median house price is $24,000 in Boston suburb. So it's strange, but I think it's from the 1960s data. So this is a famous data set from some paper. So the price is so low, 50, 60 years ago. And the crime rate, first variable, zone, some zoning, I don't know. And this is you can see the help of Boston dataset. Maybe the distance from the industrial area or something. So this is not sure. NOx is some the environmental factor, maybe the so NOx, basically the
NOx is small. It generates smog. It's a pollution.
Yeah. Yes. So the one nitrogen and the X oxygen. So that this is the harmful products of like diesel engines. And the RM is I don't really remember all the variables, but you can check. And age and distance from the city center, probably the RAD, I'm not sure. The tax rate, maybe the PT, maybe in the school, the parent, the the pupil teacher ratio, and black, I think some kind of the percentage of the black population, something. And LSTAT, I have no idea. So we have several variables. And here we consider fitting the median house value on crime rate. That makes sense, right? So crime rate is lower, then house price is higher. And also maybe the house age or the distance from the city center, those variables matter. Okay, so at first make a scatter plot, crime rate, and the median house value. So always start with descriptive statistics, the graphs and the summary statistics. And this is the graph, crime rate and the median house value. So what's the problem here? I mean, no problem to make a plot, but the what's the problem when we want to fit the linear regression? Obviously, error distributions are different depending on the X value. So here we have so many observations. Maybe, I don't know, but the too many observations. So that means the straight line is probably mostly determined by these observations. So that's a problem. If these 6 observations are removed and maybe just recorded in different places, then the fitted line or reliability of the fitted line may be totally different. So we have some problem about the skewness. Actually, this is the histogram of crime rate, and the crime rate, I think the 0 to 80, I don't know the unit, but maybe number of incidents per 1,000 people or something. And actually, this is very skewed to the right. So it's probably good to transform by concave functions such as logarithm or square root. So theoretically, this is just X values, not random. So not necessary that this should be distributed as uniformly or symmetrically, but still, very skewed data has trouble for estimation. So we make transformation by logarithm. I will try logarithm. And the median house value also, we make a histogram. It's almost symmetric, but we have some observations, some more observations here. So this is a kind of problem. Actually, this data is, I believe that the censored at 50. Probably some observations are really large, so that's why they censor at 50. So this is also essentially skewed to the right histogram, but it's truncated, and also some asymmetry around here. And here, the log of crime rate and the median house value. So median house value, you can see that it's truncated at 50. So many observations are exactly at 50. But overall, it makes some sense. We have some linear relationship. We have some trend line. So we want to fit the model, the median house value on log of crime rate. Then this is estimation result. So log of crime rate has negative coefficient. So higher crime rate, lower housing price, house price, and the relationship is significant. So that makes sense. We have 2 parameters, 506 observations, so 504 degrees of freedom. And residual standard error, 8.2. So on average, we have on average, I mean, typically that we have the error of $8,200. So our estimate is something, then we can say typically the house price in that town is the estimate plus minus 8,200. And confidence interval you can make. So intercept is actually as small as 20, as large as 22. The center estimate is 21.02. The estimate for the coefficient of log of crime rate, so negative 2.3 to negative 1.49, and our estimate is negative 1.93. So that means this is log scale. So exactly speaking, so median house price is the log of y, so log of crime rate, and the times negative 1.93 plus some constant 21 plus epsilon. So you can see maybe we put everything on exponential. So exponential of median household price, median price. Median house price is the crime rate, e to the power this, so times e to the power negative 1.93. Sorry, crime, yes. Yeah, so that's the point. And yeah, and the regression is useful, of course, because this coefficient is useful. So this is the basically equivalent test results, since this is a linear regression. And confidence interval. So confidence interval. So confidence interval gives the where is the true regression line is. And next one is prediction interval. So this means where actual observations are. And yes, you can see the lower bound and upper bound of the confidence bound and the prediction bound. And okay, so some code to make these curves. And this is the result. So the observations are, of course, the original data, and the black line is estimated regression line between log of crime rate and the median house value. And the red dotted line is the confidence interval. So the true line is within this interval. So it's pretty narrow. We have actually 506 observations, and the relationship is very clear. So actually, maybe data have some randomness, but if we observe another, we observe more and more observations, then we identify the true straight the regression line. Then that should be between this red band. And the green band includes 95% of observations. You can see that we have 506 observations. So 90% of the observations are within this. I mean, yes. So you can see that out of this range, we have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, and maybe 15, and 19, 20, and 24, and 27, 29. So 29 observations. So 29 out of 506 is about 0.06. So about 5%, right? So this is parametric estimation. So not exactly 5%, but around 5% of observations are outside of this range. Actually, maybe this one also outside, so maybe 30. So about 6%. So in typical case, maybe 13 observations here and 13 observations here. But this median the median house price is slightly skewed to the right, so that may affect this result, and this is slightly asymmetric. So next, which observations are most influential to this regression line? And we cannot really see. So no outliers, actually. Maybe this point maybe makes fitted line, intercept of the fitted line higher. It lifts the regression line a little bit, maybe. Or maybe these observations, these observations, maybe this observation, this observation, this observation. These may have a large effect. And this is the distribution of hot values. Hot values means how extreme X values are. And okay, so it's right skewed graph, but when we see the 6 largest hot values, that is around here, actually none of these are extremely large. For example, the largest one isn't much different from the 6 largest one. So I wouldn't say there are outliers, probably not many outliers, but still, okay, so this is just a practice. So we identify the 3 largest leverage values, and that is 406 and the 419th and 381st observations. And these are actually these points. So actually the right hand points have the largest one. Oh, sorry. And these points should not be selected because the Y values are not in consideration to calculate hot values. So possibility is maybe these points or these points, but actually the right hand points have more influence. Even we take the logarithm to make distribution even. Yeah, and these labels can be obtained by this code, point label function. May be convenient in some cases. Yeah, so this is the how to implement the linear regression in R. And yeah, next maybe multiple linear regression. The distance from the city center. Maybe not city center. City center, then the price should be like this. So maybe distance from some area. I don't know. Maybe we can check the R language explanation. The DIS means I cannot show on screen, but the DIS stands for the weighted mean of distances to 5 Boston employment centers. So actually the lower values are better in the sense that it's more convenient to commute. But usually if the houses are close to employment centers, that means that many people don't have a car or something. So maybe the median house value is lower and the income level is lower. So that's why we have just the small values here. And NOx, nitrogen oxides, the concentration, pp, I think the pp 10 million. So parts per 10 million, that is the unit. And the higher level, the basically the environment is not good. So this should have negative relationship with the house price. And actually it's pretty reasonable to assume a linear relationship between this. So maybe we need some transformation here, but still maybe positive and negative. So now we put these 3 predictors to explain median house value. Then, okay, so this is the regression result. All 3 variables are significant. For example, in this case, the second one, p-value of 3.15 times 10 to the power negative 5, very small number. So this means the test against test between 2 hypotheses. The null hypothesis is the y, the price is equal to log of crime plus NOx. And alternative is the y is the log of crime rate plus NOx plus the DIS. So just leave one out p-value. So if we remove the distance from the 5 employment centers, then model is almost the same or significantly worse. And actually this p-value is small, so that means the distance is a useful predictor. And the ANOVA table, this is sequential. So we compare the null model of the y is equal to intercept. And the next model is y is equal to intercept plus the beta 1 times log of prime. And next hypothesis is y is equal to beta naught plus beta 1 log of prime plus beta 2 times DIS. And H3 is everything. Then we test sequentially. And p-values are here. P-values are all significant, so that means all variables are useful. It's possible that the distance and NOx are sufficient, and actually that this isn't necessary. That is our possibility, but because we haven't tested such a model. But in this sequence, at least we can say NOx is significant. And yeah, and next we just change the order of the variables, not distance plus NOx, but the NOx plus distance. Then the sorry, I think this is wrong. I think this should be 2b, LM2b. I think this is a typo, so this is not valid. Sorry. But anyway, so that's fine. That's fine. Actually, this is just a change of order, but actually the result is the same. This is not valid, but if we change these two variables, still the results are the same, because these p-values are leave one out p-values. Order does not matter, just the remove NOx from the entire model, or remove DIS from the entire model. So actually these are the same as, even we write summary of LM2B, still the same. But the ANOVA is different because it's sequential. So here, the first variable is the log of prime, but the second one is NOx rather than DIS. Yeah, but actually the NOx and the DIS are significant in any order. So sometimes the later variables become not significant because maybe first two are sufficient to explain the house price, then the last one isn't needed. But here it sounds a little strange result. And the third one is always the small p-value, and the second one, large p-value. And it's harder to interpret, but the situation is the NOx and distance there as a single variable that does not have much explanatory power, therefore house price. But if we combine two, then it explains the situation. Probably that's the explanation. So that means realistically, if houses are close to the employment center, it's convenient. But if the environment is good enough, if the houses, the lands are contaminated by some chemicals from the factory or something, then it's not good, right? So even if distance is small. So that is probably the reason that the second one is less significant. This is a pretty uncommon situation, but that can happen. But the point is that if we change the distance, p-values are different, and also the lower variables are less likely to be significant because we have already many other predictors in the model. Yeah, the final result is the test between LM1 and LM2. So H0, this is LM1. This is the y is equal to beta naught plus beta 1 log of prime. And LM2 is this plus beta 2 times NOx plus beta 3 times distance. So we test the two variables as a set of variables. Then p-value is significant also. Yeah, so that's the. Do you have any questions for chapter 3 lab?
Sorry. No, but is there a do we do the lab, or is that going to be based on this, or when you say lab, I didn't see anything as an assignment.
Sometimes I assign some questions, but lab is actually the last section of each chapter in the textbook. So I explain the some R codes. Sometimes I use the different examples. Probably this one is different examples from the textbook, but yeah. So our implementation is the lab section. Yes.
Okay, thank you.
Yeah, and today I'm not sure how many homework quiz questions, but yes, yeah, again, so to do data analysis, always start with descriptive statistics and graphs. After that, we can do modeling and the statistical inference.